Hello and welcome to the second part of this experiment on evaluation and conclusion. In this video I'm going to be covering the evaluation of an experiment we looked at in the previous video, which was the activity of catalase, the enzyme. So let's have a look at the experiment. So here is the conclusion that we wrote up in the previous video. If you want to have a look at that again, just check out the video. So what we're going to be focusing on now is the evaluation. There are two parts to it, the evaluation of the data and the evaluation of the procedure. Okay, so the first part will be looking at the evaluation of the data. So when we're evaluating data, this is not really something that you should just leave until the end. It should be something that you should be doing whilst you're analyzing your data. Okay, so you should be evaluating your data when you're analyzing it in case you need to do more repeats or in case there's some kind of issue with the processing part of it. But once we get to the final, we're happy with our results, we can then evaluate our final data. So here is our raw data and our process data in two tables that we discussed before. So the two main kind of things that we should look at is whether the repeats support each other in terms of trends and how much variation there is. So in the previous video on conclusion, we concluded that chopping increased the rate of activity, that liver was higher than potato, and that boiling was lower than not boiling. Okay, now, how well is that supported? So if we have a look at our repeats, we can see that for the liver sample, B is always higher than A. Same thing for the potato. Okay, so those trends are the same. We can see that the boiled in both liver, C, D, and for potato, they're always the same as well. So they're always 0. Okay, and then finally, we can see that for both the liver and the potato, that the liver is always higher than potato. So for liver A is higher than potato A, and liver B is higher than potato B for all the repeats. Okay, so the first thing is the repeats support each other. Okay, you've got similar trends between repeats. Now the second thing we need to look at is the amount of variation. So when we talk about variation, we talk about, well, how much difference is there between the values between our repeats. So if we have a look at, for example, the potato, for A it's 3.8, 3.2, 3.0 with a mean of 3.3. So they're pretty similar. Same thing for B and C and D. Okay. If we have a low amount of variation, we end up having something called standard deviation. So standard deviation is just a number put on the amount of variation we have. What it actually does, it takes the mean distance of each of these values from the mean. So it calculates the difference from each of the values from the mean, and it calculates the average of that, if you will. Okay. So both of these have a standard deviation of 0.4. And if we have a look for the liver, we can see that sample B is pretty low variation with a low standard deviation, and A is higher actually. We can see actually that this is because of R1, which is something what we call, it's still within the pattern, but it's a bit out there. So it's a bit of an anomalous result. And the reason for that will be discussed in the evaluation. Okay, so the other thing that we can have a look at here is something called the coefficient standard deviation, which is essentially standard deviation in terms relative to the mean. So here you can see, of course, it's quite high, 0.4 and 0.4 is lower, but even though the standard deviation is the same here, relatively speaking, this A is higher than B. Okay, it's 12.5%, whereas here it's 5.5%. So typically values of 5% or lower are really good, 10% is still okay, 15% or higher is less good. So in our evaluation of our data, we summarize all that. So the repeats support each other and support the hypothesis as discussed in the conclusion. However, for sample A, the whole liver, the first trial was much lower compared to the second and third trials. This resulted in blah, 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 blah. One reason for this could have been a random error, which may have been caused to oxygen escaping. So here we try to explain what could have caused that error. Okay, and Then we comment on the standard deviation for the rest. For the rest of the samples, there were relatively low levels of standard deviation, less than 50%, suggesting a high degree of reliability. So the lower our standard, a low standard deviation means a low variation, which means high reliability. A high standard deviation means high variance, means lower reliability. So we can't trust the results. If we have similar results every time that we repeat an experiment, that's reliable. Okay, we can trust them. Now the second part is the, so often people actually overlook the analysis of the data, but it's incredibly important that you incorporate that as well and not just focus on the procedure. There's a couple of other things within the evaluation that I will talk about in another video, so I haven't really mentioned here, which is trend strength and statistical analysis, so there'll be another video on that. Okay. So the next part is the procedure. And when you're looking at the procedure, what you really want to look at are the strengths and the weaknesses of your experiment. And so we need to go back to what our control variables were and how well did we control them. Okay. How good was our range? If we have like a trend line, for example, with 5 independent variables values, and we're looking for a pattern, how was that range that we chose suitable for this experiment? Okay, but it's not relevant here because we don't have a linear relationship. Right, so for this experiment, we're going to start off with the thing that would have caused the most variation. So in this case, it is possible that oxygen may not have all been collected in the measuring cylinder. Some may have escaped via junctions where the seals may not have been tight. There may also have been some oxygen lost in the time between adding the potato or liver to the hydrogen peroxide in the flask and putting the bung on. So if we have a look at the setup, in this experiment, we put the hydrogen peroxide in first, then we added the potato or the liver, and then we put the bung on and connected it all. So some oxygen may have escaped here. It may have escaped in the process of putting by the time we put the stuff in and we put the lid on and the timer started. So all of that, in all of that timing, some of the oxygen may have escaped. So this could have resulted in a lower rate of oxygen production being recorded. To overcome this in future, the junction could be sealed with Vaseline, or the setup could be altered so that the potato or liver are added first, the bung is put in place, and the hydrogen peroxide is added via syringe directly through the bung. This would also overcome the issue of liver and potatoes sticking to the sides of the flask in a rush to put them in, resulting in less enzyme being in contact to catalyze the reaction and therefore resulting in a lower. So here I'm explaining what the effect of this could have been. This was likely to have been the greatest source of variation in experiments, and how likely this particular weakness, what extent it could have affected the results. Okay, so this I've evaluated it. I haven't just said this is a weakness. I've actually evaluated how this could have affected the results and explained it and discussed it. Second paragraph is another thing another factor. So something else that we tried to control was the size in terms of the mass and the surface area. How well did we control that? So the mass was 1.00 gram plus or minus 0.01 grams, which is the relative the uncertainty of the measurement, which is relatively low measurement uncertainty of 1%. So 0.01 divided by 1.00 grams. So less likely to have had a large effect. Okay, so less than 5% relative measurement uncertainty is quite low. So this is unlikely to have been a huge source of variation in this experiment. The chopped pieces were cut with a sharp knife, but there may have been a variation in the total surface area exposed to the hydrogen peroxide. And then an explanation, a larger surface area would result in more enzymes, and vice versa. There could also have been an effect on the whole piece, which were cut to size with a ruler. The uncertainty of the measurement for the ruler, or measuring the cut pieces, was 1 centimeter plus or minus 0.1, which is slightly higher. To reduce this further in future experiments for the potato, a potato slicer could be used, but this may not work as well for the liver. And a blender could be used for the chopped samples to puree them. Okay, so I've identified a potential weakness. I've actually evaluated how likely this is to have affected the results. I've used evidence to back up my reasoning. I've explained how this could have affected the results. And then I've suggested realistic improvements in order to reduce this in future. Okay. The final one is the least likely factors to the affected rate of reaction were the substrate concentration and temperature. So these are things that would have been controlled. Temperature, to a lesser extent, we can make an assumption that the temperature was the same in the room if it's done at the same time on the same day, and we monitor it with a thermometer. So although both of these are known to have effects on rate, in this experiment all hydrogen peroxide used was taken from the same batch, and the experiment was carried out at room temperature on the same day. So these were unlikely to have had any significant impacts on the results. So again, we are evaluating how much these particular factors could have affected the results.